Terrence Howard has recently brought attention to a chilling event that has resurfaced to shake our world. Oumuamua, which baffled scientists with its unusual trajectory in 2017, has returned, defying the laws of physics, speeding towards us with an unsettling intent and raising a whirlwind of questions within the scientific community. Could this be an indication of an alien presence or merely a silent observer of our delicate planet? Are we on the verge of a breakthrough in understanding? Or are we staring at our demise? Join us as we explore scientists' warnings about Oumuamua's imminent impact in 2 weeks. It shows no signs of stopping. When you hear the term alien probes, your imagination might transport you to the world of 1960s sci-fi abduction stories, where extraterrestrial beings use strange tools to examine human subjects under the haunting lights of their spacecraft. Alternatively, you might think of the enigmatic object Oumuamua, an interstellar traveler that fascinated both astronomers and conspiracy theorists with its mysterious journey through our solar system. Oumuamua, a rocky cigar-shaped enigma with a reddish tint, made its grand entrance into our solar system in 2017, becoming the first confirmed emissary from another star system to visit our cosmic neighborhood. The name Oumuamua, derived from Hawaiian, translates poetically as a messenger from afar arriving first, hinting at its cosmic significance. In the autumn of 2017, this cosmic nomad traversed the inner solar system, drawing attention not only for its peculiar shape, but also for its origin beyond our sun's dominion. Dubbed One-Eye Oumuamua by astronomers, the designation One-Eye denotes its status as the inaugural interstellar interloper, identified within our solar confines. The saga of Oumuamua began on October 19, 2017, when University of Hawaii astronomer Rob Warwick stumbled upon its fleeting presence in data captured by the Vigilant Panoramic Survey Telescope and Rapid Response System. Initially spotted 21 million miles away, its trajectory brought it within a mere 15 million miles of Earth's vicinity, offering a tantalizingly close encounter with our celestial visitor. Yet, like a wisp of stardust in the night sky, Oumuamua swiftly slipped away, propelled to a velocity of 54.2 meters per second by a gravitational nudge from the sun. Its departure marked the conclusion of a brief but momentous visit, leaving scientists scrambling to glean whatever insights they could from its passing. The window to observe the object was fleeting. Its diminutive size and rapid motion limited our opportunity to unravel its cosmic secrets. Yet, in its wake, it left a lingering sense of wonder and speculation. As it fades into the depths of space, it leaves us with more questions than answers about what other mysteries lurk in the vast cosmos, waiting to be uncovered. Are we truly alone in the universe, or is there something more waiting to be discovered? Let's find out. Probe technology has long fascinated humanity, sparking our curiosity about the vast unknowns of space and the potential for life beyond our planet. Whether these marvels of engineering originate from distant galaxies or are crafted by our own hands, probes stand as emissaries of science, venturing into the cosmic void to unravel its mysteries. These intrepid explorers, equipped with an array of scientific instruments, serve as our eyes and ears in the unfathomable reaches of space, transmitting data back to Earth via radio signals. They offer glimpses into worlds beyond our imagination, with each probe tailored to study the unique environments it encounters. Since the dawn of the space age in the 1950s, humanity has launched a myriad of probes, each pushing the boundaries of our understanding further. Yet as we peer into the depths of the cosmos, the tantalizing prospect of contact with extraterrestrial civilizations looms on the horizon. Imagine the monumental task facing an alien civilization seeking to send a probe to Earth from the distant confines of the Andromeda Galaxy. With a journey spanning 2.5 million light-years, such an endeavor would test the limits of both distance and time. To return their probe to Earth before their civilization's demise, they would need to defy the cosmic speed limit, harnessing technologies beyond our current grasp. Could these advanced beings have unlocked the secrets of theoretical wormholes or warp drives, transcending the known laws of physics? The possibilities tantalize the imagination, sparking intense speculation among astronomers and physicists alike. Yet, even if extraterrestrial engineers surmount the challenges of interstellar travel, formidable obstacles remain. Their probes must endure the harsh rigors of space, braving radiation and cosmic debris with unwavering resilience. Crafting materials capable of withstanding such extremes demands ingenuity and innovation, pushing the boundaries of material science to new frontiers. In the quest for toughness and durability, researchers strive to develop materials that defy conventional limits. Balancing hardness with resilience, these materials promise to revolutionize space exploration, paving the way for probes that withstand the rigors of cosmic voyages. Amidst these reflections on the wonders of space exploration, the enigmatic interstellar object emerges as a testament to the mysteries that lie beyond our grasp. After years of speculation, NASA's Associate Administrator for Science at the time of Oumuamua's discovery, Thomas Zurbuchen, made a groundbreaking statement in 2017. He declared that they finally possessed concrete evidence of the existence of interstellar objects. Following this revelation, another interstellar wanderer, 2I Borisov, emerged into the scene in August 2019. Originally named C2019 Q4, 2I Borisov marked the first observed instance of a rogue comet and the second recorded interstellar intruder after Oumuamua. Its discovery was credited to Borisov, a dedicated amateur astronomer and telescope maker from Crimea, on August 29, 2019. Unlike typical comets bound to the Sun, 2I Borisov boasts a heliocentric orbital eccentricity of 3.36, signifying its lack of allegiance to our solar system. It traversed the ecliptic of the solar system towards the end of October 2019. And reached its closest proximity to the Sun just over 2 astronomical units away on December 8, 2019. Notably, its closest encounter with Earth occurred on December 28, 2019. In November of that same year, Yale University astronomers were astounded by the comet's vast size, noting that its tail extended 14 times the length of our planet. They reflected on the humbling experience of seeing Earth's relative smallness against this massive celestial body. By March 2020, observations showed that the comet had started to break apart, a finding that was further confirmed in April. Unlike Oumuamua, which was notable for its unusual absence of a tail and coma, Borisov displayed typical comet features, including both a tail and a coma, a gaseous envelope around its icy core. Although the discovery of Oumuamua did not meet astronomers' expectations despite predictions of interstellar objects, it still provided valuable insights. Despite its unusual shape, it appeared to emit gases as it traveled through space, likely due to the sublimation of hydrogen or nitrogen ice from distant solar systems. Interstellar objects are often propelled into space by the gravitational forces of gas giants or significant collisions that break apart protoplanets. Early evaluations of 2I Borisov's nucleus suggested a diameter between 1.4 and 16 kilometers. Unlike comets within our solar system, 2I Borisov experienced significant shrinkage during its journey through the solar system, losing at least 0.4% of its mass before perihelion. Furthermore, the level of non-gravitational acceleration indicated an upper limit of 0.4 kilometers for its nucleus size, consistent with previous Hubble Space Telescope observations, which estimated an upper limit of 0.5 kilometers. Despite being relatively close to Earth, over 300 million kilometers away, direct measurement of its size and shape via radar was not feasible. Predicting an oscillation event required precise orbital calculations and a network of small telescopes to detect it. As the first interstellar visitor on record, Oumuamua offers a unique glimpse into the dynamics of planetary systems beyond our own. Its unusual shape adds to the mystery of its discovery. Oumuamua stretches up to a quarter-mile in length, with an extraordinary elongated shape, potentially 10 times longer than its width. This elongation surpasses that of any known asteroid or comet within our solar system, surprising scientists and offering new insights into the formation of distant solar systems. Designated 1I 2017 U1 Oumuamua, this object garnered attention on October 19, 2017, through the University of Hawaii's Pan-STARRS-1 telescope, funded by NASA's Near-Earth Object Observations program. Initially classified as a comet, subsequent observations following its slingshot past the Sun on September 9, 2017, at a staggering speed of 196,000 miles per hour, showed no typical cometary activity. This led to a temporary reclassification as an asteroid until its slight acceleration suggested comet-like behavior. At first, it was thought to be a massive cylinder, appearing to be 10 times longer than its width. However, later measurements revised this view, indicating it was more like a flattened, pancake-shaped object. Interestingly, similar shapes are found in the Kuiper Belt, like the minor planet Arrokoth, which NASA's New Horizons probe visited on New Year's Day 2019. Analysis of its light curve, tracking brightness variations during its journey, revealed its shape and dimensions. When its broadside faced Earth, Oumuamua appeared brighter. The significant fluctuation in brightness indicates its highly elongated shape, roughly 10 times longer than it is wide, with complex convoluted features, explained Meach. Furthermore, its reddish hue, similar to objects in the outer solar system, combined with its lack of dust, suggests a dense composition, likely rock and possibly metals, without water or ice. Its reddish surface tint implies ages of exposure to cosmic rays. These traits suggest that Oumuamua has been wandering the Milky Way for hundreds of millions of years, unbound to any stellar system, before its chance encounter with ours. The exact stellar origin of Oumuamua remains a perplexing mystery. However, in 2018, detailed research provided a vital clue about its journey. Tracing its path back revealed that around 1 million years ago, the object passed near 4 stars, with the red dwarf star HIP 3757 being the closest encounter. This finding suggests the intriguing possibility that it either came from this stellar system or has been wandering through space for an extremely long time. Unlike the regular orbits of planets, asteroids, and comets in our solar system, its trajectory is hyperbolic. This means it approached the Sun at such a high speed that the Sun's gravitational pull could only slightly alter its path, preventing it from being captured into a circular orbit. Traveling at a remarkable relative speed of 16.36% at 23 million miles from our star. Its journey originated roughly from the direction of Vega in the constellation Lyra. Additionally, its incoming motion deviates 6 degrees from the solar apex, which is the direction of the Sun's movement relative to nearby stars. This alignment closely matches the expected trajectory of objects coming from outside of our solar system. By mid-November, astronomers confirmed its interstellar origin after carefully analyzing observations over 80 days. One of the most notable features of Oumuamua's orbit is its exceptional eccentricity of 1.20. The highest ever recorded until 2I Borisov's discovery in August 2019. An eccentricity greater than 1.0 indicates that an object exceeds the Sun's escape velocity, suggesting it is not bound to the solar system and it's heading towards interstellar space. While eccentricities slightly above 1.0 can result from planetary encounters, as with the previous record holder C1980E1. Oumuamua's eccentricity is so high it cannot be attributed to any known planets. Even undiscovered planets cannot explain its trajectory or speed increase. For these reasons, it can only be of interstellar origin. On October 26, 2 pre-Covery observations from the Catalina Sky Survey were found, dated October 14th and 17th. A 2-week observation arc confirmed a strongly hyperbolic trajectory. In the fall of 2017, this cosmic wanderer traveled through the inner solar system, attracting attention not only for its unusual shape, but also for its origin from beyond our Sun's influence. And as stated earlier, the object was named 1I. This signified its status as the first interstellar object identified within our solar system. The story of Oumuamua began on October 19, 2017, when University of Hawaii astronomer Bob Weirich discovered its fleeting presence in data from the Vigilant Panoramic Survey Telescope and Rapid Response System. Initially detected 21 million miles away, its path brought it within just 15 million miles of Earth, offering a tantalizingly close encounter with its celestial visitor. However, like a wisp of stardust in the night sky, it quickly slipped away, accelerated to a velocity of 54.2 meters per second by a gravitational push from the Sun. Its departure marked the end of a brief but significant visit, leaving scientists eager to extract whatever insights they could from its brief appearance. The opportunity to observe Oumuamua was brief. Its small size and rapid motion limited our ability to unlock its cosmic secrets. Yet it left behind a lasting sense of wonder and speculation. As Oumuamua recedes into the depths of space, it leaves us pondering what other mysteries lie in the vast cosmos, waiting to be discovered. Are we really alone in the universe, or is there something out there yet to be discovered? Let's explore this question. The technology behind probes has always captivated humanity, fueling our curiosity about the vast unknowns of space and the possibility of life beyond our planet. Whether these engineering marvels come from distant galaxies or are created by us, probes serve as emissaries of science, venturing into the cosmic void to uncover its secrets. These brave explorers, equipped with a variety of scientific instruments, act as our eyes and ears in the unfathomable reaches of space. By transmitting data back to Earth via radio signals, they provide glimpses into worlds beyond our wildest imagination, with each probe designed to study the unique environments it encounters. Since the beginning of the space age in the 1950s, humanity has launched countless probes, each one extending the boundaries of our understanding further. As we delve deeper into the cosmos, the exciting possibility of contact with extraterrestrial civilizations becomes more tantalizing. Consider the monumental challenge an alien civilization would face in sending a probe to Earth from the far reaches of the Andromeda Galaxy. A journey spanning 2.5 million light-years would push the limits of both distance and time. To return their probe to Earth before their civilization perishes, they would need to break the cosmic speed limit, using technologies beyond our current capabilities. Could these advanced beings have discovered the secrets of theoretical wormholes or warp drives, surpassing the known laws of physics? These possibilities ignite the imagination and provoke intense speculation among astronomers and physicists. However, even if extraterrestrial engineers overcome the challenges of interstellar travel, significant obstacles remain. Their probes must withstand the harsh conditions of space, including radiation and cosmic debris, with unwavering resilience. Developing materials that can endure such extremes requires ingenuity and innovation, continually pushing the boundaries of material science to new frontiers. In the quest for toughness and durability, researchers strive to develop materials that defy conventional limits. Balancing hardness with resilience, these materials promise to revolutionize space exploration, paving the way for probes that withstand the rigors of cosmic voyages. Amidst these reflections on the wonders of space exploration, the enigmatic interstellar object Oumuamua emerges as a testament to the mysteries that lie beyond our grasp. Upon its discovery, astronomers swiftly coordinated a global effort, mobilizing telescopes around the world, including the Very Large Telescope at the European Southern Observatory in Chile, to observe and analyze the newly detected celestial visitor. The urgency was critical, requiring rapid data collection to determine key details about the object's orbit, brightness, and spectral features. Led by Karen Meach from the Institute of Astronomy in Hawaii, astronomers used the FORS instrument on the ESO telescope and combined observations from various large telescopes. Through the use of 4 different filters, they carefully examined Oumuamua's behavior, uncovering a striking discovery. Oumuamua exhibits an unprecedented brightness variation, changing by a factor of 10 as it rotates on its axis every 7.3 hours. The distinctive feature sets Oumuamua apart from any known asteroid or comet in our solar system, with its elongated shape having a length-to-width ratio far greater than any previously observed celestial body. The Hubble telescope was particularly effective in monitoring Oumuamua's path, given its ability to observe the object over an extended period. By integrating data from the Very Large Telescope in Chile and the Gemini South Telescope, astronomers obtained detailed images of Oumuamua, revealing it as a tiny speck in the vastness of space. Initial calculations of its orbit indicated that Oumuamua came from the direction of the bright star Vega in the Lyra constellation. However, because Oumuamua has been traveling through space for so long, Vega was not near its path. Approximately 300,000 years ago, despite its rapid speed of roughly 59,000 miles per hour. Astronomers believe that interstellar objects like this one pass through the inner solar system about once a year, but their faintness and elusive nature have kept them hidden until now. Recent advancements in survey telescopes such as Pan-STARRS 1 have improved our ability to detect and study these interstellar visitors. Paul Chodas, manager of NASA's Center for Near-Earth Orbit Object Studies, expressed deep interest in the discovery, describing Oumuamua as a fascinating visitor from a distant star system, unlike anything previously observed in our solar system. The exact origin of the object remains unknown. Analyses do not conclusively claim that the object is an extraterrestrial spacecraft. However, they consider the possibility seriously. It might be an alien spacecraft that accidentally landed on Earth, or it could be space debris. Alternatively, it might be an active spacecraft sent here to explore our solar system. According to Loeb, there are several reasons to consider the possibility of this object being an alien spacecraft. Firstly, its very discovery was unusual. If the object is part of a random population, finding it as we did implies that each star in the Milky Way ejects 1,000 trillion such objects into interstellar space over its lifetime, according to calculations by Loeb and his colleagues from a decade ago. Our solar system does not produce such a high number of Oumuamua-like objects. Additionally, the object's motion nearly aligns with the local standard of rest, the average motion of stars in our region of the Milky Way, which complicates pinpointing its origin. Conventional chemical rockets cannot catch up to Oumuamua as it speeds towards the outer solar system. However, sending small robotic probes with sails at high speeds might enable us to study the object more closely, potentially paving the way for a future mission. Launching such a vessel within the next few decades is the aim of projects like Breakthrough Starshot. Whether or not we ever catch up to Oumuamua, its visit provides valuable lessons. We should be prepared for future encounters with similar objects by conducting comprehensive observational campaigns. The exact nature of Oumuamua remains speculative. When gravitational forces from wandering gas giants ejected Oumuamua from its original orbit, it became clear that this was an object from outside our solar system. Before the discovery of 2I Borisov, astronomers believed that interstellar objects would resemble comets. This object was initially thought to be a dead comet, with its volatile substances like water having evaporated over billions of years, either in its original system or during its journey near other stars due to the absence of a cometary tail. However, the Hubble Space Telescope detected Oumuamua's non-gravitational acceleration as it moved away from the Sun. This phenomenon is common in comets, which emit water vapor and dust in a tail, providing them with an extra push. Yet there was no evidence that Oumuamua was releasing water or any other volatile substances typically associated with comets. There are two leading theories about this object's composition. One theory proposed by Arizona State University's Alan Jackson and Steve Desch suggests that this object is made of nitrogen ice. They theorize that it might be a fragment of nitrogen ice ejected from a Pluto-like body by a massive impact. This idea gained traction after the New Horizons mission discovered nitrogen ice lakes, such as those in Sputnik Planum in 2015. If the sun's heat caused nitrogen outgassing, it would have provided Oumuamua with the necessary boost for its observed acceleration. Because nitrogen gives comets a highly reflective surface with an albedo of 0.64, Oumuamua would have needed to be smaller than initially thought to appear as pale as it did. Jackson and Desch's calculations suggest that if the object were made of nitrogen ice, its dimensions would be approximately 148 by 144 by 25 feet. Another theory proposed by Cornell University's Daryl Seligman and Berkeley University's Jennifer Bergner suggests that cosmic rays might have interacted with surface ice on the object while it was in interstellar space. This interaction could have freed hydrogen from water molecules, creating a supply of hydrogen gas trapped in amorphous water ice. According to this theory, as Oumuamua passed by the sun, it warmed enough to release the hydrogen gas without evaporating the water ice. The hydrogen would escape at a rate of 0.4 millimeters per second, and because hydrogen gas is transparent, it would not have created a visible cometary tail. Scientists offered another intriguing theory, suggesting that sunlight might be responsible for the object's observed behavior. Their analysis indicated that Oumuamua could be incredibly thin, only 0.3–0.9 millimeters thick. This thinness might cause its non-gravitational movement due to solar radiation pressure. They proposed that the object could be a light sail, a thin reflective structure propelled by the kinetic energy of photons. This concept has been tested in space before. The Japanese Icaros probe reached Venus in 2010. NASA's NanoSail D2 orbited Earth in 2011, and the Planetary Society's LightSail craft did the same in 2015. These missions primarily aim to test sail deployment. A light sail like Oumuamua could potentially endure a long interstellar journey. What should we do if the Oumuamua space probe makes a return? Do we need to build a Corellian shipyard? Assuming something extraordinary occurred, a significant leap in itself, it's worth speculating on our actions if the asteroid space probe reappears. To construct spacecraft capable of chasing the probe, humanity must deepen its understanding of dark energy and its manipulation within the cosmos. One suggestion is to send a craft after the asteroid probe. The challenge is immense. The object has a hyperbolic excess velocity of 5.5 AU per year and will be beyond Saturn's orbit within 2 years, moving faster than any object humanity has ever launched into space. What kind of vessel would be required? How far beyond current physical theories would our endeavor need to go? Do we board the ship in space or use fuel to escape Earth's gravity and then prepare for space travel? What should be our method of travel? Solar sails or wormholes? The concept of wormholes has 3 main issues. They tend to collapse just before someone attempts to pass through. They link other universes rather than distant corners of our own, and we don't know how to construct one. Freeman Dyson previously suggested cultivating a launch pad on the periphery of the asteroid belt, akin to riding a moving conveyor belt through an airport with an allo drive. A warp bubble might achieve this. A warp bubble occurs when the imaginary space behind you on the conveyor grows, propelling you forward while the space in front of you contracts, drawing you closer. Space-time remains flat within and outside the bubble, but curves around its periphery, creating the illusion of a squeezed bubble. Since its departure, the interstellar visitor Oumuamua has been steadily moving out of the solar system. NASA has detailed how the object was accelerated to a velocity of 54.2 miles per second by a gravity assist from the Sun. Its small size and rapid speed meant that the window for observing it was brief, lasting only a few weeks. During this period, the Hubble Space Telescope provided the longest and most detailed observations. Now, Oumuamua is on its way towards the constellation Pegasus, having traveled far beyond the orbit of Neptune. It is currently passing through the Kuiper Belt, a distant region populated by icy bodies near the edge of our solar system. This remote area is filled with small celestial objects that orbit the Sun beyond Neptune. But even here, the object is beyond the reach of our most powerful telescopes. The data gathered during its fleeting visit continues to intrigue and puzzle scientists, as we may never see the object again. The mystery of Oumuamua has sparked endless curiosity and numerous theories, from its possible composition of nitrogen ice to the more speculative ideas of it being an extraterrestrial probe. Each hypothesis adds another layer to our understanding of this enigmatic object and fuels our desire to explore and learn more about the vast universe we inhabit.
Imagine a colossal machine buried deep underground, stretching across countries, with the power to recreate conditions just moments after the Big Bang. This is CERN's Large Hadron Collider, the world's largest and most powerful particle accelerator. But what if we told you that something went terribly wrong? Recently, an unexpected and inexplicable event occurred at CERN, leaving scientists scrambling for answers. Actor and science enthusiast Terrence Howard shared his insights on the LHC's latest developments, offering a unique perspective on the ongoing discoveries and challenges. The anomaly observed has stirred a whirlwind of speculation, theories, and excitement within the scientific community. What could have caused such a shocking outcome? And more importantly, what does this mean for the future of particle physics? Stay tuned as we unravel the enigma surrounding this perplexing incident at the LHC. Terrence Howard recently brought attention to a perplexing incident at the Large Hadron Collider. When CERN scientists pushed the collider to its highest energy levels, they observed an unexpected and puzzling result. Howard highlighted the excitement and speculation within the scientific community as experts proposed various theories to explain this anomaly. This unexplained result occurred when the LHC was operating at its maximum capacity. The observed data did not match predictions, leading to a flurry of activity among physicists. The anomaly has sparked numerous hypotheses, ranging from potential new particles to undiscovered principles of physics. Howard noted that the scientific community is buzzing with theories to explain this surprising outcome. Some experts suggest that the anomaly could indicate the presence of new, previously undetected particles. Others believe it might point to limitations in the current models of particle physics, suggesting that our understanding of the universe's fundamental forces might need revisiting. The implications of this anomaly are profound. If the observed result leads to the discovery of new particles or forces, it could revolutionize our understanding of the universe. Such a breakthrough would open up new avenues for research and potentially lead to the development of novel technologies based on these newfound principles. What caused such a surprising outcome? And what does it mean for our future scientific endeavors? These questions are at the forefront of the ongoing investigation at CERN. The unexpected results challenge scientists to think creatively and explore beyond the established boundaries of physics. The unexplained anomalies at the LHC highlight the ever-evolving nature of scientific discovery. As researchers delve deeper into the data and refine their experiments, the potential for groundbreaking discoveries grows. Terrence Howard's spotlight on this incident underscores the importance of continuous inquiry and the excitement that comes with pushing the limits of human knowledge. The scientific community, fueled by curiosity and driven by these unexpected findings, is poised to unravel more mysteries of the universe. Howard described the Large Hadron Collider, LHC, as a colossal machine, stretching across 2 countries and extending deep underground. Imagine a device so immense and powerful, it redefines our approach to particle physics, he explained. The LHC is not just a machine, it's a marvel of human ingenuity and engineering. Spanning a 27-kilometer ring, it lies beneath the border between Switzerland and France. This enormous structure is composed of superconducting magnets and a series of accelerating structures designed to boost the energy of particles. The sheer scale of the LHC is staggering, representing decades of collaboration among thousands of scientists and engineers from around the world. Howard highlighted how the LHC redefines our approach to particle physics. Traditional methods of studying the universe's smallest components were limited in scope and power. The LHC changes this by allowing scientists to collide particles at unprecedented energies. This provides a glimpse into conditions that existed just moments after the Big Bang, offering insights into the fundamental forces that govern the universe. The construction of the LHC is a testament to what humanity can achieve when united by curiosity and a quest for knowledge. The machine's development required innovative solutions to overcome numerous engineering challenges. From the design of its powerful magnets, which must operate at extremely low temperatures, to the precise alignment of its components, every aspect of the LHC represents the cutting edge of technology. Howard also touched on the captivating stories behind the LHC's creation. The journey to build the collider involved overcoming geopolitical, financial, and technical hurdles. It required international cooperation on an unprecedented scale, with scientists and engineers from over 100 countries contributing their expertise. The stories of persistence, collaboration, and innovation are as compelling as the scientific discoveries the LHC aims to make. Mauricio, the LHC holds the promise of groundbreaking discoveries. It is designed to answer some of the most profound questions in physics. What is the nature of dark matter? What happened in the first moments of the universe? Are there additional dimensions beyond the ones we perceive? By smashing particles together at near-light speeds, the LHC creates conditions that allow scientists to probe these mysteries, potentially revolutionizing our understanding of the universe. CERN, the European Organization for Nuclear Research, stands as a beacon of international collaboration and scientific curiosity. Its origins trace back to the post-World War II era. As Europe was recovering from the devastating conflict, there was a growing consensus among scientists and policymakers that collaboration was the key to rebuilding the continent's scientific prowess. In 1950, the renowned physicist Louis de Broglie proposed the creation of a shared European laboratory to rekindle scientific innovation and strengthen peaceful cooperation. Soon after, in 1952, 11 countries came together to sign the CERN Convention, establishing the organization. By 1957, CERN was officially up and running on the border between Switzerland and France. CERN's mission has always been to delve into the mysteries of atomic nuclei and their components. To do this, particle accelerators were essential. These massive machines accelerate particles to nearly the speed of light and smash them together, revealing the fundamental building blocks of the universe. By the 1980s, the vision for the LHC began to take shape, driven by the need for a more powerful tool to explore deeper into matter's secrets. The LHC was designed as the world's most powerful particle accelerator, featuring a 27-kilometer ring of superconducting magnets and detectors. Its construction began in 1998, a massive project that brought together thousands of scientists and engineers from around the globe. Situated 100 meters underground, the LHC was strategically placed to avoid the complex terrain of the Jura Mountains and to shield it from external influences. This underground location also avoided the high cost of surface land. In 2010, the LHC achieved a major milestone by successfully colliding particles at an energy level of 3.5 tera-electron volts per beam, an unprecedented feat at the time. After subsequent upgrades, it now operates at an even more astounding 6.5 tera-electron volts. Picture two beams of particles racing at nearly the speed of light and colliding head-on. That's the extraordinary capability of the LHC. There are 4 key collision points within the LHC, each surrounded by sophisticated detectors designed to capture and analyze the phenomena resulting from these high-energy impacts. Most of the time, the LHC is busy colliding proton beams, but once a year, it switches gears to collide heavy ions like lead, creating a special annual event. Howard passionately conveyed the significance of these endeavors. Why invest so much effort? Because the quest to understand our universe drives us to push the boundaries of science and technology. Physicists are utilizing the LHC to explore some of the most complex theories in particle physics. They are particularly interested in studying the elusive Higgs boson and investigating a large array of particles predicted by supersymmetric theories. Hadrons, tiny subatomic particles composed of even smaller quarks, are a key focus. These particles form the building blocks of protons and neutrons. The LHC, named for its ability to collide hadrons, produces byproducts that often exist only briefly and can't be studied by any other means. Each collision in this enormous underground ring is akin to a mini Big Bang, offering scientists a glimpse into the fundamental components and forces of the universe. Constructed between 1983 and 1988, the LHC's underground tunnel spans a massive 3.8 meters in width and is protected by concrete. Above ground, there is a building housing essential equipment such as control electronics, compressors, ventilation systems, and cooling devices. The LHC generates around 15 petabytes of data annually, an immense volume of information. To manage this, an international collaboration created a specialized computing grid just for the LHC, which is a technological marvel on its own. The primary mission of the LHC is to uncover the secrets of the Higgs boson, a particle long theorized by scientists, but never observed due to its high mass. The LHC's powerful capabilities were designed to produce multiple Higgs bosons each minute, like setting a trap for an elusive creature. Beyond the Higgs boson, the LHC has delved into other uncharted areas of physics, searching for supersymmetric particles and other unknown phenomena. However, the journey hasn't been without challenges. Shortly after its launch in 2008, a magnet malfunction caused significant damage, delaying operations for over a year. But from 2009 to 2013, the LHC made groundbreaking discoveries, including finally observing the elusive Higgs boson. After its first successful run, the LHC was upgraded and resumed operations in 2015, embarking on new scientific adventures. The second run of the LHC lasted from 2015 to 2018, followed by another pause until it restarted in April 2022 with an enhanced beam energy of 6.8 TeV. This third run will continue to captivate scientists until 2026. During this third run, something extraordinary occurred on July 7th. A mysterious crack appeared in Earth's magnetic field, remaining open for an astonishing 14 hours. This allowed a surge of solar winds from the sun, resulting in massive geomagnetic storms and spectacular auroras. The crack was attributed to a co-rotating interaction region, CIR, from the sun, where solar winds of different speeds interact, creating turbulent plasma structures. Experts assure us that such cracks in the magnetic field are not unusual and usually close quickly. However, recent events show they can stay open longer, allowing some space storm energy to penetrate, and potentially disrupt satellites, radios, and power systems. While our magnetic shield generally protects us from these storms, some energy occasionally slips through, similar to living in a house with a drafty window during a storm. Overall, the LHC continues to be a pivotal tool in uncovering the mysteries of our universe, with each run promising new discoveries and insights into the very fabric of existence. The LHC's operation involves not just incredible physics, but also managing vast amounts of data. Imagine a room packed with complex control electronics, compressors, ventilation systems, and cooling equipment. This high-tech environment is necessary to support the LHC's functions. However, the truly astonishing aspect is the data output. The LHC generates around 15 petabytes of data every year. To put this into perspective, 15 petabytes of data is equivalent to about 15 million gigabytes. This massive volume of information poses significant challenges in terms of storage, processing, and analysis. The data is generated from the millions of particle collisions that occur every second within the LHC. Each collision produces a wealth of information about the particles involved and the resulting interactions. To handle this immense amount of information, an international collaboration established a specialized computing grid specifically for the LHC. This grid, known as the Worldwide LHC Computing Grid, WLCG, is a network of over 170 computing centers in 42 countries. It is designed to store, distribute, and analyze the data produced by the LHC. The WLCG is a technological marvel, providing the necessary infrastructure to manage the LHC's data efficiently. The computing grid involves cutting-edge technology and innovative software solutions. Data from the LHC is first processed by the Tier 0 Center at CERN, where initial analysis and filtering occur. The filtered data is then distributed to Tier 1 centers around the world for further processing. Finally, Tier 2 centers, which include university and research institute computing facilities, conduct detailed analyses and simulations. This tiered approach ensures that the massive data load is managed effectively and that valuable insights are extracted promptly. The primary goal of the LHC is to uncover the secrets of the Higgs boson, a particle that was theorized for decades before being discovered by the LHC in 2012. The Higgs boson is essential for understanding why particles have mass. Despite its importance, the Higgs boson remained unseen due to its substantial mass, making it difficult to produce and detect with previous technology. With its immense power, the LHC can produce several Higgs bosons each minute during high-energy collisions. These collisions occur at nearly the speed of light, recreating conditions similar to those just after the Big Bang. The ability to produce Higgs bosons regularly allows scientists to study this elusive particle in unprecedented detail. By examining how the Higgs boson interacts with other particles, researchers can gain insights into the fundamental structure of the universe. The discovery and ongoing study of the Higgs boson have profound implications for particle physics. It confirms the mechanism that gives particles their mass, as predicted by the standard model of particle physics. However, the Higgs boson also raises new questions, such as the nature of dark matter and the potential existence of other unknown particles. The data generated by the LHC is crucial for exploring these mysteries. The quest to explore the unknown realms of physics with the Large Hadron Collider, LHC, can be likened to attempting to capture a rare, elusive creature, one that many believed existed but had never seen. The discovery of the Higgs boson was a monumental achievement, but the LHC's ambitions extended far beyond that. It ventured into uncharted territories of physics, probing for supersymmetric particles and other hidden phenomena that could fundamentally alter our understanding of the universe. The journey, however, was not without its challenges. Shortly after the LHC began operations in September 2008, a significant setback occurred. A magnet malfunction caused extensive damage to the collider, halting experiments and necessitating a shutdown for over a year. This incident underscored the complexity and delicacy of operating such a massive and sophisticated machine. The repair and recovery process was arduous, involving meticulous work to replace and recalibrate the damaged components. Despite this initial hurdle, the LHC resumed its operations from 2009 to 2013. During this period, the collider made several groundbreaking discoveries, the most notable being the identification of the Higgs boson in 2012. This discovery was a major milestone in particle physics, confirming the existence of the particle that gives mass to other particles, as predicted by the Standard Model. It was a momentous achievement that validated decades of theoretical work and experimental efforts. Following this success, the LHC was temporarily shut down in 2013 for a series of planned upgrades. These enhancements were designed to increase its power and improve its detection capabilities. The upgrades included strengthening the collider's magnets, improving its cooling systems, and enhancing the data collection and processing infrastructure. The LHC returned to operation in 2015, entering its second phase, which lasted until 2018. During this second phase, the LHC continued to explore new frontiers in particle physics. Researchers focused on searching for evidence of supersymmetry, a theoretical framework that extends the Standard Model by predicting a larger family of particles. The collider also investigated other exotic phenomena, such as dark matter candidates and potential extra dimensions. After another break for additional upgrades, the LHC resumed operations in April 2022. This third phase features an enhanced beam energy of 6.8 TeV, allowing for even more powerful and precise collisions. This increased energy capacity is crucial for probing deeper into the subatomic world and potentially uncovering new particles and forces. The current phase of the LHC is expected to continue until 2026, promising to deliver even more captivating discoveries. Scientists are particularly excited about the potential to find new physics beyond the Standard Model. This could include evidence for dark matter, insights into the asymmetry between matter and antimatter, and further understanding of the strong force that binds quarks together in protons and neutrons. The LHC's journey has been marked by both significant challenges and remarkable breakthroughs. From its early setback due to a magnet malfunction to the historic discovery of the Higgs boson and beyond, the LHC has continually pushed the boundaries of our knowledge. Its ongoing upgrades and current phase of operation hold the promise of even more revolutionary discoveries, continuing to captivate and inspire the scientific community and the public alike. But on July 7th, during its third run, something truly remarkable occurred. Picture Earth's magnetic field as a protective bubble around our planet. On that day, a mysterious crack appeared in the shield. This wasn't just a brief glitch. It remained open for an incredible 14 hours. Imagine a window left open on a stormy night, letting in the cold winds. This crack allowed a surge of solar winds from the sun, causing massive geomagnetic storms. The result: spectacular displays of auroras lit up the sky. Fans of Stranger Things might liken this event to the emergence of the monstrous Vecna, humorously suggesting he came through this crack. While that's just playful speculation, the breathtaking auroras were a real and undeniable visual treat. Think of the search for dark matter like a treasure hunt where, instead of finding the actual treasure, you uncover maps that lead to it. These clues might just be hints for more significant discoveries in future experiments. Here's an intriguing twist: dark matter. This mysterious substance, though invisible, constitutes a significant part of our universe. Some of the new particles detected by the LHC might be linked to dark matter. However, these particles are so elusive that they rarely reveal themselves directly. It's akin to trying to see the wind. You can't see it directly, but you can observe its effects, like leaves rustling in the breeze. At the LHC, scientists look for other particles behaving unusually, which might suggest the presence of these invisible ones. The challenge lies in the fact that these signs are often incredibly faint. Detecting them is like trying to hear a whisper in the middle of a loud rock concert. The subtle indications of dark matter are easily drowned out by more dominant signals. This makes the task of identifying dark matter particles exceptionally difficult. However, with the upgrades introduced in Run 3, the LHC's detectors have been enhanced to pick up these faint signals more effectively. These upgrades include improvements in sensitivity and resolution, allowing scientists to detect even the slightest anomalies in particle behavior. This enhanced capability increases the likelihood of capturing elusive particles associated with dark matter. These advancements mean that scientists are better equipped than ever to uncover new clues about dark matter. Each detected anomaly, no matter how small, brings researchers one step closer to understanding this enigmatic substance. The ongoing experiments and data analysis are crucial for piecing together the puzzle of dark matter, potentially leading to groundbreaking discoveries in future runs of the LHC. The search for dark matter at the LHC is like a meticulous treasure hunt. While the actual treasure remains hidden, the maps and clues gathered along the way provide invaluable guidance. The elusive nature of dark matter presents significant challenges, but with the LHC's upgraded detectors, scientists are now more capable of picking up the faint signals that could reveal its secrets. As research continues, each discovery brings us closer to unraveling one of the greatest mysteries of the universe. But wait, there's more. Plans are in motion for an even larger and more ambitious project. The Future Circular Collider, FCC. Think of it as the LHC's bigger, more powerful sibling. This enormous particle accelerator could come with a price tag ranging from 9 to 21 billion euros. However, not everyone agrees with this investment. Some argue that such a substantial sum could be better spent on other significant scientific endeavors. For instance, why not build a giant radio telescope on the moon's far side or launch a space-based instrument to detect gravitational waves? The proposed Future Circular Collider has sparked considerable debate within the scientific community and beyond. While many see it as the next logical step in particle physics, others question the return on such a massive investment. Critics, like well-known physicist Sabine Hossenfelder, argue that this colossal machine might not deliver the groundbreaking discoveries we hope for. It's akin to investing in an ultra-powerful telescope that might not reveal any new stars. They suggest that alternative projects, such as developing advanced telescopes or space-based detectors, might yield more immediate and diverse scientific benefits. Despite these concerns, the FCC represents an extraordinary leap in our quest to understand the fundamental nature of the universe. If built, it would dwarf the LHC, providing unprecedented energy levels and collision rates. This increased capability would allow scientists to explore uncharted territories in particle physics, potentially uncovering new particles and forces that could revolutionize our understanding of the universe. Meanwhile, the LHC is gearing up for Run 3 and even a potential Run 4, promising plenty of exciting science on the horizon. Each phase of LHC operations has brought us closer to solving key mysteries in physics, such as the nature of dark matter, the behavior of antimatter, and the fundamental forces of nature. We are in the midst of a cosmic detective story, piecing together clues one by one, with each phase promising new insights and discoveries. The Future Circular Collider represents both a bold vision and a contentious investment in the future of particle physics. While its potential to unlock new realms of understanding is vast, so are the costs and uncertainties associated with its construction and operation. As the scientific community continues to debate its merits, the LHC's ongoing and future runs ensure that our journey of discovery is far from over. We stand on the brink of new breakthroughs, driven by our relentless curiosity and the ever-advancing frontier of science. Think of these developments like episodes of a gripping series, and we're about to binge-watch the latest installment. One recent surprise involved an anomaly in Earth's magnetic field that stayed open much longer than expected. Imagine discovering a hidden door in your house you never knew existed. This unexpected crack in the magnetic field allowed solar winds to flood in, causing geomagnetic storms and dazzling auroras. What more might we uncover next? Max Laughlin, a prodigious thinker, proposes a rather alarming theory. He suggests that experiments at CERN could have caused a shift in our reality, leading to what is known as the Mandela effect. According to Laughlin, the high-energy particle collisions at CERN might have created a ripple in the fabric of space-time, nudging us into a slightly different version of our universe. The Mandela effect refers to instances where many people remember events or details differently from how they actually occurred. Named after the false memory of Nelson Mandela dying in prison in the 1980s rather than in 2013, this phenomenon is believed by some to be evidence of our transition to an alternate reality. For example, people might recall famous logos, quotes, or historical events differently than they are documented. Laughlin's theory posits that the extreme energies and conditions created during CERN's particle collisions could potentially disrupt the very fabric of space-time. These disruptions, he suggests, might result in our consciousness shifting into a universe almost identical to ours, but with subtle differences. Hence, the collective false memories. However, while Laughlin's theory is fascinating and captures the imagination, it remains speculative. The scientific community largely views it with skepticism. The experiments conducted at CERN are indeed at the cutting edge of physics, exploring the fundamental particles and forces that make up our universe. They push the boundaries of our understanding, but there is no concrete evidence to support the idea that they can create alternate realities or shift our consciousness into them. The work at CERN has led to numerous groundbreaking discoveries, including the confirmation of the Higgs boson, but its impact on the fabric of reality as we perceive it remains firmly within the realm of theoretical speculation. While the Mandela effect continues to intrigue and puzzle people, it is more likely a result of the complex workings of human memory and cognition than a consequence of particle physics experiments. With the emergence of various theories and public concerns about the experiments conducted at CERN, it's natural for people to worry about safety. One of the primary concerns at CERN involves radiation. To minimize exposure, CERN has implemented stringent safety protocols. Personnel working with particle accelerators and detectors are equipped with dosimeters, which constantly monitor their radiation levels. Areas where radiation hazards exist are strictly controlled, and access is limited to trained personnel. Additionally, the engineering designs of the facilities incorporate robust shielding materials to contain radiation effectively. Chemical safety is another critical aspect. CERN handles a variety of hazardous substances, and they have meticulous procedures for their handling and disposal. This ensures that chemicals are managed safely to prevent any accidents or environmental contamination. Electrical safety is also paramount, with regular inspections and adherence to international standards to prevent electrical hazards. Fire prevention systems are rigorously maintained, with regular drills and safety checks to ensure all equipment is functioning correctly. The safety of CERN's workforce is a top priority. Comprehensive training programs are in place to ensure that all personnel are well-versed in safety protocols. Safety drills are regularly conducted to prepare staff for emergencies such as fires, chemical spills, or radiation leaks. CERN also has an on-site medical service to address any health-related issues promptly, ensuring quick response times in case of accidents or medical emergencies. CERN is equally committed to environmental safety. They take significant steps to minimize their environmental footprint, managing waste responsibly and monitoring air and water quality to prevent contamination. CERN's operations include rigorous environmental monitoring to ensure that their activities do not adversely affect the surrounding area. CERN extends its safety commitments to the public. Access to the facility is controlled to minimize risks, ensuring that visitors are safe at all times. CERN maintains open lines of communication with local authorities and actively engages with the community to address any concerns. They hold public forums and provide detailed information about their safety measures to reassure the community and stakeholders. In conclusion, CERN's commitment to safety is comprehensive and multifaceted. From radiation containment and chemical handling to electrical safety and environmental protection, every aspect of their operations is designed with safety in mind. By prioritizing the well-being of their workforce, the public, and the environment, CERN demonstrates its dedication to conducting groundbreaking scientific research responsibly and safely. Thank you for being with us. Let us know what you think about these discoveries in the comments below, and we'll see you in the next one.